Okay. Um, okay, I think the recording started. Okay, so welcome everyone. So we will be continuing our discussions on max margin classifiers from last lecture. So I hope you did a little bit of revision of perceptrons and max margin classifiers. So let's start. I will share my screen. Okay, just give me 1 second. Okay, so maybe let's start with a very quick recap of like what we discussed in the last lecture. So we looked at perceptron, which is a very simple algorithm where the idea is to go through the examples one by one and see if they satisfy the perceptron criteria. Otherwise, like you take a gradient step, right? So this was the algorithm. Like it's a very simple algorithm where you initialize with some W randomly, and then you repeat until all the data points are correctly classified. Like you're going to go through these examples one by one. And if it is correctly classified, you don't do anything. If it is wrongly classified, you do a correction, right? And we also discussed like, well, I mentioned that this perceptron algorithm should converge if your data is linearly separable. And then we discussed a bunch of issues with this algorithm. So the first issue is if the gap between the two classes is too small, it's going to take more time. That is unavoidable, right? Like on there were two other issues. Like the second issue was when the data is linearly separable, then there are many solutions possible. So now it's not clear which solution is the right solution or which solution, like there's no unique solution by perceptron, right? Like, so for example, in the figure that we see here, like, so if you start with this particular red line, right, then you will end with this red line, right? Similarly, if you start with the green line, the leftmost green line, then you will end with the rightmost green line, right? Like so now both these solutions, the red solution and green solution, are valid solution, and we don't know which one is the right solution, right? Like so both has zero training accuracy, and depending on where you start, you're going to get different solutions in perceptron. And then there was also the final issue, which is the issue that when the data is not linearly separable, then this algorithm will not converge, right? Okay, so now in the previous lecture, we started discussing about how to avoid the second issue, which is the issue of having multiple solutions, right? And we discussed what is called as the max margin classifier. So the idea of max margin classifier is to come up with a classifier like a decision boundary which has maximum margin, right? So for example, in this example that I have here, there are three options, 1, 2, 3, right? Now we would prefer the second solution over the first and third solution simply because it has maximum margin with the nearest neighbors, like nearest data points, right? So now to formulate this idea, so we also wanted to define margin mathematically, right? So now what is margin? Margin is the perpendicular distance between the decision boundary and the closest of the data points. Okay, so now in this case, like I draw this red line. Now what is the closest data point? So probably the closest data point is the green one, right? So now this is like, this is what closest in one side, this is closest in the other side, and probably the closest is the green. So now the gap between the green and the red line is the margin. Okay, so then we also remember from chapter 5 that if you have a line which is y of x is equal to 0, okay, and you have a point, you want to find the perpendicular distance between this point and the line, then that is given by y of x by mod w, right? So this is from our discussion on geometry of linear decision surfaces, right? And we also observed that like we only care about margins when all the data points are correctly classified. When the data points are correctly classified, then t of n, y of xn should be greater than 0. So the distance is actually given by this formula, right? Now, given that we have this definition for the perpendicular distance between the points, now we can define margin mathematically. So margin is basically the perpendicular distance to the closest point from the data set. So we are interested in finding those parameters W and B, so argmax W and B, which maximizes the margin. The margin is defined separately by this min function, right? Like, so the margin is minimum out of all the examples, like whatever the perpendicular distances. Okay, and we found that W is independent of this n, so we take it out. And this is the objective function that we want the max margin classifier to solve, right? Or satisfy. Okay, this is where we stopped. Is there any question before we begin? So there is a question in the chat. The perceptron algorithm is designed only for binary classification problems. Okay, so that's a good question. So I think the version that we discussed in the class is for binary classification. I am not sure if there are any extensions to multi-class classification. But we know, okay, so I'm sure there are extensions, like I just don't know the names. But if you remember our discussion on one versus all, so you could take perceptron and do a one versus one perceptron classifier for multi-class problem, or do a one versus all classifier, a perceptron classifier for multi-class problem. So you can extend these algorithms by yourself to multi-class problems. Okay, is there any other questions before we start our discussion on how to solve this problem? Maybe if you have any questions, you could also do a hand raise. Okay, so if there are no other questions, let's begin. Okay, so I'm going to rewrite the margin definition. So what is margin? Margin is basically the perpend. Okay, is this function convex? Okay, so that's a good question. So we will come to that soon. Okay, so once I formulate, for now I have given you the higher level objective. So we are going to construct the optimization problem soon, and then like you yourself will know whether it is convex or not. I will also tell it. Okay, but that's a good question. Okay, so margin is basically the perpendicular distance to the closest point xn from the data set, right? And max margin classifier is basically trying to find this W and B. Okay, so arg max of W and B such that, like, what are you maximizing? You're maximizing the margin. Now, what is the margin? Margin is basically this min over all the examples, T of n, W transpose phi of xn plus B divided by W, right? So now this whole thing is the definition for margin. Now you're maximizing the margin, but that itself requires a minimization problem inside. Okay. Now, as I said before in the previous lecture, direct solution for this optimization problem is very complex. Okay, so we are not going to solve this problem directly. So what we are going to do is we are going to convert this problem into an equivalent but much easier problem to solve. Okay, so now how am I going to do that? So we are going to do this based on this crucial observation, okay, which is basically If I just rescale W to KW and let's say B to KB, okay, if I just rescale my parameters, okay, then the distance from any point xn to the decision surface, which is given by the formula that we have seen, which is T of n, y of x of n divided by, right, is unchanged. Okay, so I will prove why this is the case. But the observation that we are making here is if I just rescale W to KW and B to KB, then the distance of the point xn from the decision surface is not going to be changing. Okay, so why is that the case? Let's try that. It's a very simple algebra. So you take T of n, y of xn divided by 1W. Okay, so now I'm going to substitute. Okay, maybe first let me expand y, right? Let's say this is basically T of n. What is y? Y is basically W transpose phi of xn plus b, right? So now I'm going to substitute W to KW and B to KB. So let's see what happens. So this becomes T of n, W becomes KW, okay? So KW transpose phi of xn plus KB divided by, the K comes out of the norm, so it's K times W. Okay, so now this becomes T of n. You can take the K outside, right? And W transpose phi of xn plus by S divided by K non-W, right? So now the K cancels. So now you can see that even if I rescale W and B, the rescaling actually cancels out each other. So like we just get the same distance. Okay, now we are going to use this freedom, okay, to set T of n multiplied by W transpose phi of xn plus b is equal to 1 for the point that is closest to the surface. Okay, since it doesn't matter like if I rescale W and B, so I'm going to rescale them in such a way that the margin, like which is basically the minimum, the distance, like the minimum distance between the decision surface and the first data point, right? I'm going to set the margin to 1. So this is without loss of generality, right? I'm not making any assumption here, like because I have already proved here that even if I rescale, the solution is same. So I'm not making any assumptions. So without loss of generality, I could actually set the margin to be 1. Okay, so how do I do that? So for example, let's say I have a bunch of cross and a bunch of circle. Okay, so now if this is my decision surface, then probably this is the margin because that's the closest when compared to this, right? So this is the margin. Now I'm going to set this margin distance to be 1. Okay, and then like rescale the rest accordingly. Okay, so basically in this case, all the data points will satisfy the constraint that T of n W transpose phi of xn plus b is greater than or equal to 1. Okay, now it's going to be equal to 1 for the examples in the margin, and it is going to be greater than 1 for every other example. Okay, now this representation is known as the canonical representation of the decision hyperplane. Okay, so now this is a constraint, right? So now let's take this constraint separately to the next page. Okay, so maybe I would also copy my example. Okay, so now this is a constraint, and we are going to make a couple of definitions. Like we're going to define a couple of definitions here. Okay, so for data points, there's a question: is the margin is equal to 2 times closest distance? Okay, so margin. Okay, so margin is not twice the closest distance. The margin. Okay, the definition of margin is basically. So, okay, this is the definition of margin. Like you find the point which is closest to the decision boundary, and the distance between that point and the decision boundary is the margin. Okay, now in this case, like in the same cartoon example that we have here, there are 2 points which are nearer to the margin, right? Like this circle point and the cross point, right? However, margin is just the distance between the black line and the circle, because that is the closest. Is that clear? Okay. Okay, so now for data points for which this equality holds exactly equal to 1, right? Now we are going to call that data points as places where the constant is inequality. This inequality constant is said to be active. Okay. Now for data points for which the equality does not hold. Okay, so this is the first point is when the t of n y of xn is equal to 0. Okay. On the other hand, like if t of n y of xn is equal to 1. Okay, so it's greater than 1. If it is strictly greater than 1, then those are the places where the constraint is, sorry, this is constraint, is said to be inactive. Yeah, it's constraint, sorry. That's my mistake. Okay. 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 So now I can understand Emmanuel's confusion here, because as per this definition, okay, at any point of time there will be at least one constraint which is active. Okay. So let's do an example. So I have a bunch of circles here. Okay. And I have a bunch of crosses here. Okay. So now if I draw a line like this as my decision boundary, okay, now what is the closest to this? I know this is a very trivial poll, but let's still do this poll. So what is the closest class to this decision boundary? Is okay, so let's say let's take 2 candidates, this candidate and this candidate, right? So now I'm going to do a template poll. So A for circle and cross, like B for cross. Okay, so I'm going to, this is a very trivial poll, so I'm going to stop it fast. So, okay, so we'll stop it. Okay, so all of you, almost all of you, 99% know that this is, the circle is the right thing, right? So, okay, so now this is the definition of margin. Okay, now I'm going to call this as my margin. Okay, now you can see that this circle lies exactly in the margin, right? Now if I put the same margin to this side too, okay, you see that every other example other than the circle is outside the margin, right? So now this is 1. Okay, now if you just look at how much this thing is lying, this is definitely greater than 1, right? So basically for this particular data point, the constraint is active. Okay, and for this particular data point, since it is greater than 1, the constraint is not active. Okay, so now if you remember, okay, so there is a question. Could you please explain the distance to be 1 in this case? Okay, so I think Ronald's comment is valid too. Okay, so that's my bad usage of words. Okay, so now this is not the distance. Okay, so this is t of n multiplied by y of xn. Now we set this t of n multiplied by y of xn to 1 for the closest data point. Now, similarly, you rescale for the rest. So that's why the other one is greater than 1. Is that clear? Okay. Okay, so now when I start trying different decision surface for my max margin classifier, right? Like, so max margin classifier says you find you find a line such that the margin is maximum, right? Okay, so now I'm going to kind of, well, I wish I had an animation to do this, but I'm going to kind of copy this example to kind of simulate how learning is going to happen. Okay, so to do that, I'm going to erase all these things. As much as I can. Maybe it's wrong. Okay, so let's say I have something like this. Okay, so now if I put a line here, now this is the margin, right? So I want to maximize the margin. So I'm going to move this line further down. So this line, this is the margin. Then probably I'll slowly move this line somewhere here. Now this is the margin. The margin is maximized, right? Then I will move this further. Okay. Now you see that this is no more the margin. This is the margin. Cross has become the margin because cross has come closer to the decision boundary, right? So now you see what is happening. So you will be moving your line between the two classes until you find this one specific line. Okay, so I'm going to remove all these lines until you find this one specific line, which is exactly in between these two classes. Okay, so now in this case, your margin, sorry. In this case, this is your margin, which is 1, right? So now you can see that once you find the solution, okay, so once the maximum margin is achieved, there is going to be at least 2 constraints. So once max margin solution is achieved, okay, then you have at least 2 active constraints. Okay, so you will have 1 active constraint from the circle class and 1 active constraint from the cross class. Okay, so these 2 are active constraints. So the moment you have 1 active constraint from one class and from the other class, then you have found the max margin solution. Okay, but remember, this is just at least. So for example, there could be another circle here, there could be another cross here, right? So there could be more than one example in the margin for both the classes. So that is possible. But you need at least 2 active constraints. Okay. Yeah, at least 2 active constraints. Is that wrong in the notes? No, it says at least 2. That's correct. You need at least 2 active constraints. Rest of them are inactive, right? Okay. So now, given this new formulation, I can write an equivalent optimization problem, which is much simpler to solve. Okay, so we're going to look at the modified optimization problem. Okay. Now, before we do that, okay, so there's a question about rescaling. So what kind of rescaling we did is we found that we can actually rescale W to KW and B to KB. Basically, you rescale all the parameters by B and there's nothing changing. And that was the crucial observation which helped us to come up with this reformulation. Okay, so now if you go back to your equation, okay, so I'm going to maybe copy paste this for reference. Copy. Okay. Okay, I'm sorry, this is not the modified. This is for reference. Okay. Okay. So now we are going to modify this. So remember that like we have already defined margin is going to be always 1. Right? So now this term in the margin. So this is going to be always 1. So I don't need to do this anymore. So instead my objective function now is basically argmax, okay, over just the 1 over W term. Okay, I don't need the numerator. Argmax of A comma B, sorry, W comma B, W comma B. Okay, now there is a new constraint added, subject to T of n, W transpose phi of X of n plus B is greater than or equal to 1 for n is equal to 1 to n. Okay, now this is my modified objective function. Okay, so now instead of having this as an argmax, I could also write this is argmin, right? So all I have to do is argmin W comma B. Instead of 1 over W, I'm going to do, this looks very much like the L2 regularization that we have, right? So that's why we are just reformulating it. Subject to T of n, W transpose phi of X of n plus B is greater than or equal to 1 for n is equal to 1 to n. Okay, so now this objective function is this is my modified optimization problem. Okay, okay. So now someone asked this question in the beginning, right? Like, so whether this is a constraint one is 1, but the corresponding distance is 1 over W. Yeah, that is right. That is right, Ian. So that was my mistake. Like I kind of confused the definition, and like I kind of confused the margin and the distance. Okay. Okay. So now this is my modified objective function. Okay. So now note 1. We have a couple of points here. 1. So this is actually a quadratic programming problem. Okay, why is this a quadratic programming problem? Because we want to minimize a quadratic function. Okay, subject to a set of linear inequality constraints. Okay, so this is a special case of convex programming. So we have a unique solution for this problem. Okay, so there is a unique solution. Okay, now, second note. Maybe this is a question, first of all, for all of you. So you see the objective function. It is just 1 over 2 W squared, right? I don't see the bias parameter in the objective function, but the argmin has B. So what is happening here? Any idea? Maybe hand raise or chat. Yeah, so as Krunal points out in the chat, the constraint actually has B, right? So the second note is it might appear, okay, that the bias parameter B has disappeared from the optimization. Okay, but that is not true. It's not true. Why? Because it is implicitly there via the constraints. Okay, because any change that you make to W in the optimization problem, you need to change the constraint accordingly. Like you need to change the B accordingly to compensate for that. Okay, so the B still exists in the optimization problem. Okay, okay. So now this is a constraint optimization, right? Like, so if you remember how we used constraint optimization in L2 regularization or L1 regularization, we could actually take a Lagrangian formulation for this so that we can compute gradients, right? So I'm going to copy this. Okay, and we are going to do a Lagrangian formulation for this. Okay, so my Lagrangian formulation, L, is going to have a new parameter A, which is going to be responsible for every constraint. Okay, so now this is basically 1/2 W square minus summation over n is equal to 1 to n an times the constraint. So the constraint is basically T of n W transpose phi of xn plus b, okay, minus 1. Is that clear? Okay, so now let's just call this as equation 2. We are going to use this again. Okay, okay. So now where A is equal to A1 to AN, right? Now this is greater than or equal to 0. This is the Lagrange multiplier. Okay, so remember that there is actually a minus sign in front of the Lagrangian term because we want to minimize with respect to W and B, but maximize with respect to A. Okay, so the sign is important. So depending on like whether you have like depending on what type of inequality constraint you have, like the sign is going to change. So in this case, like you want to minimize with respect to W and B and maximize with respect to A. So this is going to be minus. Okay. Okay. So now this is my Lagrangian function. Now this is what I want to minimize, right? How do I minimize this? I could compute gradients, right? Like, so I could ask what is dou L by dou W. Okay. So if I differentiate it with respect to W, I'm going to, from the first term, I'll get W minus, from the second term, the minus 1 disappears because there's no W term. But the first term exists, right? In the first term, like it's going to become summation over n is equal to 1 to capital N, an T of n. You differentiate W transpose phi of xn, you get phi of xn. Now this whole thing is equal to 0. Okay. From this, I get answer for W. W is basically summation over n is equal to 1 to capital N, an T of n, phi of xn. Is that clear? So let's just call this as equation 3. Similarly, I could also compute dou L by dou B, right? Now, what is dou L by dou B? So the first term doesn't have B. It's only the second term which has B, right? So this is basically minus summation over n is equal to 1 to capital N, an times Tn times B, right? So when you differentiate A and T and B, it just becomes A and Tn is equal to 0. Or in other words, summation over n is equal to capital N, A and T of n is equal to 0. Okay, let's just call this as equation 4. Okay, okay. Now we are going to substitute this 3 and 4 in equation 2, okay, to get our final objective function. Okay, so we are going to substitute equation 3 and 4 in 2. Okay, so let's call that as L of A. Okay, now L of A is given by, now look at the first term. The first term is half W square, right? Like, and now this is what W is. So if I do a square of this, I'm going to get half summation over n is equal to 1 to n, summation over m is equal to 1 to m. Sorry, m is equal to 1 to n. So that's a typo in the notes. an, am, t of n, t of m, phi of xn transpose phi of xm. So all I have done is I substituted this w in the first term. Okay. Similarly, I could substitute the same w in the second term, right? So now that becomes minus summation over n is equal to 1 to n, summation over m is equal to 1 to n, an, am, t of n, t of m. It's kind of same thing, right? Phi of xm, right? And so this is for this part. Okay. So then you have the second part, which is basically summation over an multiplied with b, like summation over an tn multiplied with b, right? So that part will become 0 because of equation 4. Okay. Then you just have the final part, which is summation an because of the minus 1 term. Okay. So now this becomes plus, sorry, plus summation over n is equal to 1 to capital N. Yeah. Okay. Now this is what we have. Now you see that the first term and second term are same. It's just half. One is half. One is minus one, right? So now this becomes max over L hat of a is equal to summation over n is equal to 1 to n an minus 1 over 2 summation over n is equal to 1 to n summation over m is equal to 1 to n an am tn tm. Okay. K of x and xn, okay, where K of xx dash is defined as phi of x transpose phi of x dash. Okay, so I just took this thing, the dot product, and made it as K. Okay, so now this K is also known as the kernel function, which we will revisit later. Okay, so now this whole function is subject to constraints. A of n is greater than or equal to 0 for n is equal to 1 to n, and there was also another constraint which was summation over n is equal to 1 to n, a of n, t of n is equal to 0. Right? Now, this is also a quadratic programming problem. Okay, now this problem is actually the dual problem of my first problem, which is also known as the primal problem. Okay, now one can either solve this problem to find w and b, or you could solve the dual problem to find a, and once you find a, you can use that to compute w and b. Okay. Now the question is, why do I need to have these two different problems, right? Like, so what's the advantage? So maybe let me just put them both together in one place. So then we could try to understand the advantages of one over the other. Okay, so no, sorry. This is my primal problem. Okay, now I could also have the dual problem. Okay, I think I've managed to fit both in one place. Okay, so now what's the advantage of having these two formulations, right? Like, so before we discuss the advantage, so I want to tell some general things about quadratic programming problems. Okay, so now both are quadratic programming problems, right? Like, so both are QP problems. Okay, so if you have a QP problem with m variables, okay, then the solution for this problem has order m cube computational complexity. Okay, so this is not an optimization course. This is a machine learning course. So we are not going to try to solve these problems. So we have just formulated this optimization problem, and we are going to use standard QP solvers available from the optimization community to solve this problem. Okay, so now even though we are not going to solve this problem, like, so what we should understand is a QP problem. To solve a QP problem, you need order m cube computational complexity, where m is the number of variables. Okay, so now let's look at the primal and dual. Now, what are the parameters of the primal problem? Can anyone answer in chat? Like, so what are the parameters of this primal problem? W and B. Okay, now what are the parameters of the dual problem? A, right? Okay, so now if you look at the primal problem, this is the problem over the parameters of the model. Okay, parameters W and B of the model. Okay, on the other hand, the dual problem is a problem over the Lagrange multipliers. A, right? Now, let's say there are m parameters in the model. Okay, maybe let me move to the next page. So let's say I have a model which has m parameters. And let's say my data point has n data examples in my data sets. Okay, now if the number of examples is much larger than the number of parameters, okay, then it is easy for us to solve the primal problem. Okay, however, if the number of parameters is much larger than the number of examples that you have, then you have to solve the dual problem to save time and computation, right? So if you are using any standard packages like sklearn, like for max margin classifiers, you will actually have an option to solve primal or dual. So depending on your data set, if you have more data points than the number of features, you should go for solving the primal problem. On the other hand, you should go for solving the dual problem. Okay, so there is a comment by Krunal. So Krunal, maybe can you raise hand so that I will let you speak? Okay.
Yeah, I was wondering, you said the computational complexity is cube in terms of number of variables. So doesn't it depend on number of constraints at all?
Where? Like, can you repeat your questions?
When you are describing the computational complexity to solve a quadratic problem, quadratic
Okay.
programming problem.
Yeah.
Yeah. I don't know, where did you put that?
Okay, so
Yeah,
here.
there. Yeah, here.
Okay.
So you said it's order of m cube in the complexity is only on in terms of number of variables. So I can have any number of constraints.
Okay, that's a good point. I need to verify, but at least in this case, you can see that there are all roughly equal number of constraints for both the problems, right?
Okay.
So maybe the complexity is dominated just by the number of variables, but I will verify the dependency with constraints and get back to you.
Okay.
Okay, that's a good point. Okay, so now this is the reason why we have two types of formulations here, right? Okay, but there is a question. So how to find W and B after solving the dual? and finding an, right? So in the primal problem, like I'm solving for W and B. So I get W and B, I get the classifier. But in the dual problem, I'm solving for an, right? So in this case, I'm just solving for an. Now, given the values of an, how do I compute my W and B, right? So to do that, we already know the equation for W, right? Like we solved that W is basically equal to summation over n is equal to 1 to capital N, an. Okay, so T of n phi of xn, right? So this is something that we have already derived, right? So now we have the value for W. We got W, right? So now y of x is given by W transpose phi of x plus b. This is my classifier, right? Now I know the value for W, so I can write this as summation over n is equal to 1 to capital N, A of n, T of n. There is a phi of x dot product with phi of xn. So we have already defined this as a kernel. So this becomes kernel of xn plus b. Okay, let's just call this to be phi. Okay, now we still don't know how to compute b, right? So to do that, we are going to make use of what is known as KKT conditions. Okay, so I believe that like you had this as part of your reading when you are reading about Lagrange multipliers. But the basic idea here is that the dual problem should satisfy the KKT conditions. Okay, so this is named after Karish Kuhn Tucker. Okay, so we are not going to get into the optimization theory details here. So we are just going to list those three conditions. You're going to take it as given. Okay, so the conditions are this. Your slack variables, sorry, your constraint variables, an, your Lagrange multipliers, an should be greater than or equal to 0. Okay, and T of n, y of xn should be greater than or equal to 0. Okay, and well, maybe I did a mistake here. Just give me 1 second. So my constraint, okay, so I think maybe I made a mistake. So T of n, y of xn minus 1 is greater than or equal to 0. Okay, and the third one is a of n. The first one multiplied by the second term is equal to 0. Okay, so now these are the three conditions. Now what does this mean? This basically means that for every data point, okay, either a of n should be equal to 0 or t of n y of xn should be equal to 1. Okay, so what does this mean? This means that your Lagrangian multiplier is it's either your Lagrangian multiplier is 0 or that data point is in the margin, right? Like t of n y of xn is equal to 1 only for data points in the margin. Okay, so basically any point for which a of n is equal to 0, right, will not appear in the sum. 5. Okay, so we'll take a minute to finish this so that then we go for break. Okay, so now if you remember this equation 5, so this summation, even though it's over all the data points, it's not really over all the data points. It's only over the data, all the points for which a of n is not equal to 0. Okay, so basically if whenever a of n is equal to 0, then such data points play no role in making decisions or predictions. Okay, so the remaining data points for which t of n, y of xn is equal to 1, right? So these data points, they actually lie on the max margin hyperplane. Okay, now these data points are what we will call as the support vectors. Okay, now to give you, like, to go back to the same example, let's say I have a bunch of circles and a bunch of cross. Okay, now if this is my max margin, then the max margin goes through, this is my 1. Okay, now these 4 examples, 2 crosses and 2 circles, right? Now these are known as the support vectors. Okay, once you train your max margin classifier, now to make decision, you're going to use this equation to make decision, right? So now this equation just needs those support vectors in the first term. Bias, we still haven't found how to compute bias. We will do it. But what is interesting here is that once the model is trained, okay, a significant portion of data points can be discarded and only support vectors are retained. Okay, so I still haven't told you how to compute B. So we are going to see that after a short break. So since we are stopping at 140, we will resume at 150. Okay, so I'm going to stop the recording.